take care of the post-lunch session, but it's more difficult to take care of the pre-lunch session also, right? When we are waiting for lunch or talk, lunch, right? Always. Okay. So yep, thank you. Yes, I use this. Yep, thank you. So the topic which I am going to cover today is the mixture of whatever I am doing at IIT Hyderabad with my students group. So can critical minerals recovery be a sustainable process? And we are going to discuss about the opportunities and challenges focusing only on resource recovery from e-waste. And so to give an outline, so I start with what is critical mineral, because already you guys are attending this session for past few days. I'm not going to spend too much time on that. But here I will introduce how these critical minerals and the e-waste managements are interrelated, and the opportunities and challenges I'll discuss with the themes of research, technology, environment, economy, society, and legislation. And finally, I'll try to figure out few points that can be connected with e-waste based resource recovery, especially critical minerals. So this case study is basically the solid waste management case study that we have conducted on few cities, but I'll try to cover only one city at least and try to connect how those lessons are helpful in determining this kind of studies. So to give a brief outline, so critical minerals, there must be a lot of repetitions in this particular slide. So because of this economic value and the risk associated in this supply chain, so few minerals are categorized as criticality, and those minerals are called as critical minerals. And so in India, we are having this critical minerals value mission. And if you are seeing that, the 5 pillars, it starts from exploration, mining, then midstream, downstream, and the final one is recovery and resource recovery and recycling. So this recovery and recycling is what I am going to focusing the e-waste. So whatever I am going to talk today is going to be on the critical minerals recovery and the valuables recovery only concerning the e-waste, not any other things. So we all know that e-waste is continuously rising. So tons of e-waste is every day generated by every country, and the global e-waste generation is also continuously increasing. And when we see the life cycle of any e-waste, so it starts from the raw material extraction. So here the raw material will be extracted from okay. I need to connect. Reverse. I'll put it. No issue, I'll put it. Okay. There is no pointer. No, actually, next is working. This is using this, right? Okay. Yeah, it's working. So any e-waste, so it starts from the raw materials for its production. The electronic materials will be produced, then it will be marketed, consumed, then it will be used completely. Then finally it goes to disposal when its life meets its end. And if it goes to disposal, then obviously all the critical minerals or valuables which are associated with that e-waste also will go to disposal mode, and we need to go for new product. That is how we are using the electronic waste. So this kind of e-waste, so there is no management. So all this, whatever is being produced, becomes the waste. I think this is better. I think you can see that, right? So all this can be considered as waste. But the point is moving towards circular economy. So we need to make sure that as much as possible, we try to recover the critical minerals and valuables from the e-waste. So that's what we have seen in the previous slide. So because of its economic value and the shortage of the supply chain or the disruption in the supply chain, we need to obviously figure out the secondary source of any critical mineral. So here comes e-waste, also one of the bright chance. So here, because we are going for recycling and reusing, so again, all the raw materials, instead of taking it from the ore, we are having a secondary source where portion of these materials can be taken back from the e-waste itself, and again it comes back to the cycle. So now e-waste becomes resource. So now it is called as e-waste resource. So and it has a huge potential of recovering the resources, especially critical minerals and precious metals. And when it comes to circular economy, two things we need to focus. One is it reduces the need for mining new critical minerals from the ore source. The second one is decreases the environmental and health risk associated with any dump site, because obviously when we are disposing the e-waste into disposal sites, that ends up in a lot of environmental damage and health risk, so that we are getting rid of. So the main point is having this understanding. Let us come to the main point. The main point is about the discussion on the opportunities and challenges associated with critical minerals recovery from e-waste. So here, not just critical minerals recovery from e-waste, we are talking about the sustainability. Can we really achieve the sustainability or not? So to give a background of what is sustainability, so you all might have know, but I just give a recap of what is sustainability. So the basic three pillars are environment, social, and economic sustainability. But most of the projects, whatever we are doing, okay, so if these three overlaps, then the middle portion, so that is called sustainable project. Okay, so but whatever the projects we are doing, so mostly can satisfy two of these pillars, missing one. Say bearable projects can meet social and economic viability, but it will completely remove the environmental protection part. Similarly, equitable project, so whereas the economic benefits are completely ignored, and so viable project, whereas the social acceptance is completely ignored. Okay, so with this one, the another measure of sustainability is the sustainable development goals. So we are having 17 sustainable development goals. Each one talks about a specific sector and the specific theme. Now, the question is, when we are talking about the critical minerals resource recovery from e-waste, so among this, which SDG is mostly connected or directly connected? Climate change. Okay, that's a good guess. Any other thoughts? The question is, so we have 17 sustainable development goals. Among these, with which sustainable goal the critical mineral resource recovery from e-waste is directly connected, are very much connected?
Life on land, sustainable life on land, clean water and sanitation.
Clean water and sanitation. Okay, that's again a good guess. Any other thoughts? Responsible consumption and production. Okay, number 12. You also goes for that. Industry. Okay, industry and infrastructure. 7 is more connected. 7 is energy, clean energy. Yes, clean energy. Okay. 11. Sustainable cities and communities. Okay, that is connected. Okay. So the question is most connected. Okay. 8 is connected. Okay, 8 is connected because it is talking about decent work and economic growth. 9 is connected. Okay. 11 and 13 are connected. Okay, already those are in the list. Remaining 6 only, right? Already we have included 11. Yeah. So the most connected one is responsible consumption and production, production and consumption. So remaining are also connected, but the most connected sustainable development goal with any resource recovery from the waste management is responsible production and consumption. And obviously directly or indirectly you can connect, because all the targets if you go through, then obviously you can connect it with one or another way. So having this understanding of what is the basic pillars of sustainability and the sustainable development goals, so I have split the further opportunities and challenges related discussion on these 6 themes. I start with research, then go towards technology and development, then environmental protection and impact related issues, economic benefits, society and legislations. So I start with research. Okay, so this is today's morning's data. So this data is taken from Scopus. So you can see very clearly. So we are conducting a lot of workshops, a lot of conferences on critical minerals, right? This becomes a hot topic in recent days. But if you see the literature review, so the publications, number of publications, if you see, so till 2008, 2009, the publications number were around thousands. This is with the keyword search of just critical minerals recovery. Okay, I did not include the keyword e-waste. Okay, and from 2012 it started, 2012 2013 there is a jump, then you can see a steady slope, then after 2016-17 you can see the rise is kind of very sharp, and now everyone is like working on critical minerals and precious metals recovery from different waste components, urban mining. So then if you look at, so there are publications, we understood that the publications are steadily growing. Now let us go to what is the theme. Okay, so on what basis these publications are kind of built up. So if you make that analysis, what I understood is the 21% goes to environmental science and engineering, and the 13% goes to chemical engineering. Again, 13% goes to earth and planetary sciences, and next to that, two other components. One is agriculture and biological science and energy people. So all these people are very much interested and working on critical minerals recovery. Okay, and the remaining all like chemistry, other engineering disciplines, material science. So they are also working on it, but in a very less percentage. And if you see the number of journals or what type of journals they are publishing, also very much matching and overlapping with the analysis of what we have seen here. So most of the publications are environmental, chemical, earth and planetary science, and agriculture and energy background. And next comes the publication type. Okay, the publication type, if you see, as we have expected, most of them are research article followed by review article, then the book chapters. But when it is about the critical minerals recovery, it should be more of technology development, more of technique development, novelty, right, innovation. So those kind of things are expected. So if you see the patent search, okay, very less, around total, this is past 25 years data, past 25 years, there are like 250 number of patents were published under Scopus. This is from Scopus. Okay, so that means that we are working more on publications, but when it comes to technology and when it comes to innovation, invention, still we need to improvise a lot when it comes to critical minerals recovery. And that becomes the challenge, that becomes the opportunity. So why it is challenging? Again, let us look at the country-wise data. So surprisingly, so the similar kind of pattern is what I observed when any resource recovery from solid waste management also. That is why I have made the case study also based on solid waste management. So here the observation, country-wise observation is the top countries. You can see top 10, 12 countries are listed. India is in 4. Exactly in waste management and resource recovery from waste also, India is in 4th place. And but if it is not only about the placing, it is about what is the ratio. Say United Nations and China, if you see, the number is, the difference is not that much. But 3rd place goes to UK. You can see it is like 1/4 of what US is publishing. And we are also in the same group. So UK, India, Italy. So we are all in the same group, slightly decreasing in numbers. But you can see United States and China, they are kind of, their publications are almost 4 times, 5 times higher than us. Okay, that too, if you see year-wise data, still we can do a lot of analysis on this part itself. So research-wise, what is lacking? What is the challenge part? One is new findings are there in Indian community, but how many of us are really publishing? How many of us are really taking the data into publication? So that is something which is very challenging. And as I have mentioned, most of this data were taken from Scopus. So few of the documentations may be not under the Scopus search, maybe I would have missed it. And the second is technology transfer. So many CSIR labs, they are also working on critical minerals recovery, but they work mostly on technology transfer rather publications or other things. And the funding support. So most of the articles, they need article processing charge. So generally Indian funding systems, we don't we don't get fund to publish a paper in a paid journal, but most of the foreign countries, they do get a lot of funding just to publish their data. So that is the very big difference between countries like US and China versus India. And so this is one of the biggest gap. And the another thing is researchers approach also towards a problem statement. Like, people work on a particular problem, then they will get a next project, they need to move to the next project. That is how the life goes, unless otherwise a student is there who is very much committed, or the faculty itself or a researcher itself is very committed. So in that way, most of the data were available, but not in a published format. So this becomes the missing puzzle. So moving forward, so obviously when there are challenges, obviously there must be an opportunity also. So moving forward, so as I have mentioned, all this keep on mentioning that interdisciplinary collaboration is very mandatory when it comes to the themes, research themes like critical minerals recovery from e-waste or any waste or urban mining. So we need to include environmental engineers, chemical engineers, policymakers. Why policymakers? Why policymakers? To get suggestions, publications, permission. Okay. So policymakers give us permission. Okay. Any other thoughts? Even I have included health scientist, NGOs. Why health scientist here? Environmental impact. Okay, environmental impact has to be dealt by environmental engineers. But here what I mention is health. The people who are working on health. Okay, it is not only about the environmental impact, it is about the health risk also. Most of the e-waste management end up in lot of health risk that I will show in the next slides, and I will discuss on that part also. And the research fund allocation and the timely release is very important for any such documentation to happen immediately after the research is over. Then we need to really focus on patents, technology transfer, and the global partnership. So now a lot of project calls are coming up with the bilateral proposal calls, but we need to be very careful about the confidentiality and the data leakage part also when it comes to international collaborations. So with this background, which is more of research output, let us talk about the technology. So when it comes to technology, e-waste starts from waste generation. Then you need to take care of the transport of e-waste. So collection center, sorting and classification, and electronic recyclers. Then you need to apply the 10 steps in R's, that we call it as R ladder in circular economy. So it starts from refuse, recycle. So recovery is the final step. So you apply everything, then it comes to the actual recovery part. Okay, so after dismantling, you go for material or mineral recovery. So you have multiple routes, pyro routes, hydro routes, bio, electro. So many routes are there. And my group is working on hydrometallurgy and electrochemical and hybrid techniques. So I will discuss that part also. So looking at the technology, if we talk about the challenges, it starts from the directly scaled or applicable technology is completely lacking. So even though we are developing a lot of lab scale and bench scale reactors, upscaling the reactors is one of the major challenge because of multiple reasons. But the good news is that many of the research groups are working on this, and these are on the way. So very soon we will be overcoming this part. The second major challenge with any of the critical mineral resource recovery, critical minerals or resource recovery from e-waste is the well-defined infrastructure. So here, what do you mean by well-defined infrastructure? You can see the supply chain. So the supply chain starts from generation of e-waste. Where do we generate e-waste? It may be at your home. It may be at your office. So do you know we have a e-waste collection bin in IIT Hyderabad? How many of you know that? And where does it locate? Where is it located? Any idea? We have e-waste drive cycle, and e-waste collection drive, right? And we have a solid waste management system. How many of you are aware of that? And as a part of that, we collect e-waste also. And we have kept a e-waste collection bin in academic block A. Yeah. So basically, the infrastructure may be available or completely missing, right from the generation, transport, collection center, sorting and classification. sorting and classification and all, we have lot of problem statements to solve, and then the dismantling and before goes to metal or minerals recovery technique, there are multiple steps that needs to be taken care of, multiple pre-processing steps that needs to be taken care of. Those are completely missing. And the another thing is the proposition of any e-waste itself is lacking. Say we have PCBs, we have types of PCBs. We have RAMs, we have types of RAMs. We have batteries, we have types of batteries. So from the preposition, what is the composition and what is the value of each mineral, how much quantity each mineral's presence are there, what kind of technology we need to follow so that we can recover one by one. So this kind of awareness is completely lacking, though we have a good technology available when we are dealing individual things. And the final challenge in front of us is the understanding about the circularity concepts itself. So there are 10 steps in circularity concept when you are trying to recover anything from any of the waste as the source. So you need to follow and you need to figure out which R I need to follow so that the maximum recovery can happen within the efficient way and within the economic benefit way. So that is completely lacking, and most of the people who are working on e-waste management and resource recovery are ground level workers who doesn't have any background of how does it work, how this system work. So the basic understanding is completely missing. And coming to the positives, the opportunities. So opportunities wise, so we need to go for a fast sorting and dismantling units. We definitely need to develop which can fit for any of the e-waste. So it has to be like tailor-made. Say different types of PCBs comes in, it should be it should take care of any PCB. It should not ignore anything. It should not exclude anything. And the second opportunity lies at better product design, which has the scope of circularity. So, you must be seeing that. So in I think 2-3 years back also we have these cables, different cables. So you buy a new mobile phone, you have to buy a new cable, right? Charging cable. But now we are slowly incorporating these policies, which kind of facilitates the e-waste generation reduction. So they are coming up with a common or one in all kind of type of port, right? So those kind of designs has to be encouraged to again fit into this circularity or ladder in the circularity. And we are working on the final concept, resource recovery, for better functionality without compromising the environmental protection. Okay, so here, what do you mean by better functionality without compromising the environmental protection? What do you understand from this term? Say we are having hydrometallurgy. Okay, so say we are having 99% of gold. So when we are going for 99% of gold, are we recovering only gold or are we generating something also? So byproducts and waste, right? So this may have its own impact on environment. So if you remember the 3 pillars of sustainability, the one of them is environmental protection. So the aim of hydrometallurgy is to recover, to leach out the substances. So you are reaching 99%, but somewhere you are compromising the environmental protection. So there should be a balance between both, and never this environmental protection should be compromised. And you need to go for higher functionality. So always we want high functionality but no environmental impact. So this is what the ideal condition is, and our group is working on that. So we are looking for developing techniques which gives high functionality or high performance and which gives low environmental impact. So we are aiming towards net zero and zero discharge in resource recovery from e-waste. So we are working on these 4 major themes. One is e-waste component specific leaching process using eco-friendly solvents. The second one is separation of high purity target valuables. So remember, high purity target valuables, we are using 2 methods. Both are based on membrane. First one is multifunctional membrane and second one is hybrid membrane system. So what is the difference between this multifunctional membrane and the hybrid membrane system? Both sound same, right? Say, I'll give a clue. Hybrid system means it is integrated. So can you guess now how it will be different? What difference between this hybrid and multifunction? Are you guys so hungry? Okay. So multifunction membrane system is a membrane which can do multiple functions. Okay, that can separate, that can do sorption, that can do complexation. So it's a membrane. Membrane itself can perform multiple functions. The another thing is hybrid system where membrane also kept, but the system works on multiple modes. Say we have membrane, we have cationic exchange membrane, we have anionic exchange membrane, you have anode, you have cathode, and in one chamber we may do some chemical precipitation, in another chamber we may do some complexation, so that the critical minerals moves in the right direction. So every chamber you get the separated metals with high purity. So that is the hypothesis of this kind of research, where you integrate multiple techniques into a single chamber with multiple compartments, so that you get not only the leaching but also the high purity critical minerals. Okay, and the third one is simultaneous e-waste management, process wastewater treatment, and resource recovery. So this one I'll explain. And the fourth one is life cycle analysis and sustainability impact assessment. To start with, so this is something that we have conducted around a year back. So I there are multiple results we got, but all these results were under review, so I cannot show all the results, but I can show you what kind of research we are doing. So here, the first row and the second row, the difference is the first row, the ram boards are shredded as such. The second row, ram boards are kind of dismantled, and we have taken only the tails. And that tail is being, from that tail, the critical minerals or the precious metals were leached out. So here, the leaching agent may be aqua regia, which is a reference, thiourea, which is again used in many of the small scale and medium scale industries, and eco-friendly solvents and DES. So we are trying all these things, and we try to do the ICP analysis. And what we understood is, instead of going as such RAM boards, if we go for individual component wise, we can really look at different composition, and every component has one or another critical mineral or precious metals very high in concentration, and obviously they have their own hidden blocks also. Say RAM ICs, if you see, nearly 4.69% of copper is there, but you can see the silica is also there. So what happens if you have silica and if you have copper in the same system? Can we go for pyro? Can we go for hydro? What happens? Any idea what happens? So what happens to silica? So in shoes, whenever we are buying shoes, bags, we have these silica balls, right? What does it do? What is the purpose of that silica balls? What does it absorbs moisture? So basically, when you add water, immediately what happens? It becomes bulge, and what happens? It will not allow the chemicals to, or the techniques to, or the functionality to work on the target compound. So here the target compound may be copper, so it will not work on it. So you need to certainly remove that, then go for the resource recovery. So you get all these ideas. Also, if you are interested in, say, Ag and palladium, then you need to focus on RAM MLCs. If you are interested in copper and copper, then you may need to go for the board, as such board. Okay, so it gives a lot of ideas. And if you see, different minerals, different metals behaves differently for the same leaching agent, and different leaching agent also differently behave for the same critical mineral or precious metal. So with this, two MTech theses were over, and both the publications were under review. And the next work, what we are doing, it's an ongoing work. My second PhD student is working on it. So what his work is, many of you might know that we have a program on e-waste resources engineering and management, MTech program, right? You guys know it? Okay, so we are connecting that program with CMET. So CMET, they are doing a lot of e-waste based resource recovery techniques, and once we have visited, we get to know that they are generating a lot of process wastewater. Okay, so the process wastewater from lithium ion battery unit and the solar cell processing unit. And when we try to, so they were looking for the wastewater treatment because their focus is completely on the recovery portion. They were not worrying too much about the wastewater that is being generated. They are just letting it allow to the nearby sewer line. So what we have done is we have taken that wastewater and we try to check, is there any possibility, because it's highly acid or highly alkaline in nature, that will completely change the characteristics of any wastewater. So can we do something on the wastewater treatment? That's what the motto was. Then when we have tried analyzing the wastewater sample, we figured out that at least 20 to 40% of resources or target minerals are wasted along with the wastewater that is being generated. So that means what? Still we can recover. So one is you can offer treatment, you can allow everything to get wasted. Another one is you can offer treatment plus resource recovery so that the resources can be recovered and the remaining things can be treated off. So having this as the problem statement, we started working on developing a novel hybrid membrane system that concurrently facilitates the wastewater treatment and the resource recovery of all the critical minerals and the precious metals. That's what the aim. So now my second student is working on. So let's see how does it work. So why it is so complex? Okay, because if you look at the lithium ion battery process wastewater and solar cell process wastewater, you can see I have highlighted all the numbers which are kind of critical minerals: cobalt, lead, nickel, here cobalt, copper, right? But if you see the other substances, TS, BOD, COD, what is BOD, what is COD, what is TS? Biochemical oxygen demand, chemical oxygen demand. So total solids, suspended solids, total nitrogen, right? So when you are having more total solids, more total suspended solids, again the same thing only. So even if you apply any chemicals, even if you are allowing it to pass through a membrane system, or if you are trying to apply an electrochemical technique, so all these suspended solids acts as a like interfering substances. So basically it try to reduce the performance and the efficiency and the functionality. Basically, it will not allow you to perform the actual function that has been intended to perform. So, and the COD and BOD, that is another problem that we need to deal with. So, it's a high complex nature and acid water, which has high organic pollutant with elevated COD. So, the difference between BOD and COD is BOD is really easy to handle because everything is simple compound, but COD is complex compound. You really don't have any idea that what is the source of the COD and what is really offering the COD. So depends on how big the molecule is, how complex the molecule is. Obviously, the treatment process is also goes quite challenging. So one side the treatment is quite challenging, the other side parallelly you need to take care of the recovery also. So high solid content, significant valuable concentration. So all this together, we try to go for a series of membrane systems, but hybrid membrane system, because as I have mentioned, you need to do multiple things together. So you need to go for a membrane system that can help parallelly with the treatment and the resource recovery. But here, again, here the aim is to again meet net zero and net zero discharge. So you may ask me one question. Do you ask? Do you have any questions to ask? So membrane system, and I'm saying net zero. So the major problem with any membrane system is huge amount of water loss. So you have RO system at our home, right? So you need to definitely connect it with electricity. You need to continuously provide the electricity, then only the RO functions. Similarly, every 1 liter you take, at least half liter will be wasted. So that means that it is an energy intensive process, and it itself generates a lot of wastewater, lot of reject. Then how come it can be a net zero and zero discharge membrane hybrid system? It's not possible, right? So we try to make a imprinted membrane, so polymer of intrinsic microporosity. So it's a porous polymer which has a lot of air gaps. These air gaps can be filled with the selected chemicals. So basically here the movement of critical minerals from one side to another side moves based on the stripping solution and the concentration gradient, but not the pressure. Okay, so with that, we have tried developing, and we could succeed in developing the membrane so far, and we could design the reactor also. And the another problem with this membrane is, so when you have a mixture of solution, say you have here, you can see it is not just one. You have, forget about the BOD, COD, total nitrogen, all the pollutants. If you see the minerals and the metals, it's mixed. You cannot say you cannot just focus on one. So you need to really develop the membrane system. If you want to go for a high pure resource recovery system, then obviously you need to very much selectively choose the chemicals in such a way that it will target one or maybe two or three from the mixture solution. Then you can go for the further things. Okay, this is another one challenge that is in front of us now, and we are trying to solve it. And the next works, which is about the multifunctional membranes, in which the membrane is a standalone system. You don't have anything. So it's a membrane will do all the function. Okay, maybe you need to externally support it with the other systems, but you don't need to have a very big reactor with the chambers, multiple chambers. So here what we have done is we have worked with ceramic membrane, we have worked with polymeric membrane. Okay, so the difference between ceramic membrane and polymeric membrane, what are the differences? Any idea? One is made up of ceramic material, another one is made up of polymeric material, right? Pore size? Big pore size? Okay. So ceramic and polymeric, pore size and all we can control. Okay, so basically membranes are of microfiltration, nanofiltration, and ultrafiltration. And if it is only the pore separation phenomena, and if it is other phenomena, then it may be RO and FO, forward osmosis and reverse osmosis. So all this can be designed using ceramic material and polymeric material, but the real difference is ceramic membranes are stable, like rigid. Okay, it will not be flexible like mold. Like you have a part, right, ceramic part at home, so it is not flexible, whereas polymeric membranes are like your cloth, you can fold it. And polymeric membranes can be fiber kind of structure, it can be sheet kind of structure, it can be spiral kind of structure, you can make it into any shape as you wish. So that is advantage of polymeric membrane over ceramic membrane. But the disadvantage of polymeric membrane over ceramic membrane is ceramic membrane's lifespan is huge. Okay, you can clean it, you can use it like your lifetime. Your kid will grow up, still your membrane will work. But polymeric membrane, you will be definitely knowing your RO system. Definitely, you need to clean once in a while. Even a small stretch in the pore will not allow the membrane to do its function. All the things will get escaped. So that is the difference between polymeric membrane and ceramic membrane. So keeping this basic understanding in our mind, so we have started with ceramic and polymeric membrane. So this research we have started around 5.5 years back. Yeah. And this is my first PhD student's work. And he started applying it for separation of pollutants from water, but slowly we are applying it for separation of critical minerals from process wastewater, and even group of like mixed solutions. From mixed solutions, how can we separate using different polymers, different ceramic membrane system. So here what we do is, one is membrane works on pore exclusion, pore size rejection based separation. When we add more material, say you coat it with sorbents, you coat it with complexing substances, what it does is it can selectively pick the target molecule from the mixed feed stream. So now even your mixed feed stream has n number of molecules based on what kind of complexing substances you have coated on your membrane. It can selectively choose, and it will not allow the other substances. It will allow only this to pass through. So now from a group of from a mixed solution which has n number of mixed metals, n number of metals, now you can separate only 3 or only 4. So ideal is 1. Okay, so that is how we started working. The same functions we have applied for polymeric membrane also. So we have established facility, and we know all the do's, don'ts on how to make a membrane, how to go for optimization, depends on what kind of pollutant or material you need to separate from a mixed stream, how to operate a system. So all these are very similar for both of these, but still the reactor design and how you need to allow the feed stream and what kind of optimization parameters you need to take care of will be totally different for both the cases. Okay, yep. So This is something I want to highlight under technology part. So we have completed research, we have completed technology, then comes the environment part. So I'll quickly complete the other 4 parts. The environment part, here I wanted to highlight that the previous time itself I have mentioned functionality versus impact, right? Risk. So you need to definitely work on the performance, but the other side you should be really not compromising the environmental protection part to meet the sustainability. So now you guys are from chemical engineering background, right? So any control volume, if something goes in, so inside the control volume, there are a lot of things are happening, right? So reaction may happen, accumulation can happen. Then you will be having an output. So this output in a manufacturing system or in a treatment system, this output may be product that is what we wanted to have. But unintentionally also something will come out which we did not aim, but still has the economic value byproduct. Then waste at that moment it doesn't have any value or use. So this waste again can be solid waste, liquid waste, and air emissions, right? So whatever chemicals we use, everything comes out. That is how the system functions. That so you must have done the mass balance and the energy balance, right? In the previous class you must have done all these calculations. So based on what is going in, what kind of resources you need to feed in, what kind of emissions are coming out, what kind of solid waste it is being generated, what is kind of liquid waste it is being generated, we can do the life cycle analysis. So this is an example of how silica can be recovered. This is a supply chain example. So we have done 4 different cases and we have done the life cycle analysis. So life cycle analysis is a basic calculation which can consider all the masses involved, all the masses come out, and ends up in giving all the information related to environmental risk, health risk, resources, also resources depletion. So to give an example, global warming. So when I asked you the question SDGs, which SDG is the most the resource recovery is being connected with, right? So the first answer I got is climate change. So climate change is connected with global warming. So how do you measure a particular technique or particular technology is having an impact on climate change or reducing the impact on climate change? So you need to measure it, right? So that is how we measure using life cycle analysis as the tool. So you can see here case 1, case 2, case 3, case 4. You can clearly see case 4 is what we need to go forward if you are very much interested in reducing the climate change. But again, I did not talk about the functionality here. Say if the functionality is also say for case 4 it is the highest, then obviously we can close our eyes and we can choose and we can go forward. If climate change and the functionality is your expectation. In case if acidification or eutrophication, so these are very much environmental related concepts. So I will go to carcinogens. Carcinogens, what is carcinogen? Cancer causing substance. So obviously the number of people who may get affected or who may get cancer if they are exposing themselves to such waste, such emissions. So now again you see there is a very big difference. Global warming and carcinogens, even the order wise both are same, but if you see the pattern, both are different, because case 1 and there it's a slope, steady slope, but here it is a exponential kind of, right? So basically case 1 is having the highest potential to cause cancer if people are exposed to such kind of technique. So people are exposed to such kind of technique. Who will get exposed to such kind of technique? The people who are really working on that, the people who are really taking care of the acid drainage, the people who are really handling the chemicals. So they also should not get cancer or any health risk. So if you want to make sure that the professional safety or work, what do we call work safety in workplace safety, then we need to obviously go for the case 4 situation. So based on this kind of analysis, so we have done multiple types of life cycle analysis for different scenarios, different techniques of resource recovery from e-waste, and this is one such sample. So we need to always check functionality versus impact. Then we need to go for which one has to be definitely environmental protection should not be compromised to meet the sustainability. So that is the ultimate thing. So next comes economy. Economy, always I explain with this figure. Okay, this figure is like we are talking about critical minerals recovery and critical minerals extraction from ore. So seawater also has all the critical minerals. Seawater has everything. All the minerals, critical minerals, precious metals, it has everything. So why don't we focus on critical minerals recovery from seawater? Sea is like 70% of earth is water, seawater. Instead of focusing e-waste, ore, we can focus on seawater, right? But why don't we do it? Why can't we do it? Because of economic viability. So how much amount is present, that matters. What kind of technique you need to apply, that matters. How much you can get and what is the benefit you are getting, that matters. So all this, so easy way is cost and benefit analysis. So you can see there is a clear line, that red color line. So right side of the red color line, whatever comes in, those are economically feasible resource recovery using a particular technique. I did not mention what technique it is. Okay, a particular technique. Whatever comes left side, you can see gold, silver, germanium, cesium, lead, barium, everything comes left side. Even the concentration is very high. So you can see the x-axis. You can see the concentration is high and the price is also high, quite high. Aurum, gold is at the topmost. But still, from seawater, if someone is trying to extract the gold, this particular technique is not environmentally beneficial. Okay, so you will end up in more loss rather the benefit. So definitely no one will be interested in investing money on this particular technique to recover gold from seawater. Okay, so when we are trying to develop our own technique, it is very important to understand the environmental cost benefit analysis. Also, one is environmental impact and another one is techno-economic analysis we need to do. So definitely we need to calculate what is the investment we need to make, infrastructure we need to make, operation and maintenance cost. Definitely you need to supply certain chemicals, energy, water, all these things needs to be supplied, then maintenance cost. Then there may be waste. Again, that waste has to be again taken care of. So, and the main point is environmental damage that a particular technique can cause, because none of the technique you can quote that it will cause only zero impact on environment. The moment you generate a waste, the moment you want to take something out of something, you need to definitely give energy. You need to definitely expect some waste or byproduct to come out of that. So obviously, in this case, there must be a minimal chances that environmental damage cannot be escaped. But this environmental damage into cost accounting itself is a very big hurdle. So around 2 days back, we got a very big manual which converts the environmental damage into cost. Say subsidies we get, right? Flood comes, all the farmers will get subsidies. How do they calculate? They have a certain protocol. Similarly, mining activities are happening. A lot of people are losing their home. Environment is completely getting degraded. Agricultural land is completely becoming infertile. So they need to get some subsidy. How does that calculation goes? So similarly, for environmental damage also, there is a calculation basis, and every time it's get revised. And Indian system also, we just developed that manual. And a lot of indicators also we are having, but for this particular problem statement, we need to really validate it. And the society and legislation, I'll just go quick. So obviously, when we are going for any new technology development, we will end up in high living standard, and we are getting rid of health risk, we are getting rid of environmental impact. We are moving out of mines and trying to see waste as the secondary source to recover critical minerals. So all these are positive points. Similarly, legislations also, we need to have a lot of policies. The rules has to really encourage people to use the minerals which are recovered from the secondary source rather the ore. So you need to put high tax there. Here you need to give some tax related incentives. So you can make all these things to have and to make the market available and beneficial for critical minerals recovery from secondary waste like e-waste. So now the case study what I have mentioned. So this is a case study. So you must have aware of smart cities mission, right? Smart cities mission. So smart cities mission, they have done multiple projects and they have selected 100 cities and they have given every city few crores to work on few projects. Okay, so this is one of the I mean the smart city mission is over now, and they want the IIT to conduct this sustainability impact assessment study. So they wanted to know, because of this mission, because of the projects implemented, what is the change that has been made. Is the city really developed as a smart city, or where does it lacking? What is the new knowledge? People's life, is there any improvement? Is there any economical benefit? Is there any environmental benefit? So they wanted to do this kind of study. So there are two problem statements I have taken. One is solid waste management and another one is local air quality. So why I am showing solid waste management, if you remember, I have shown you the slide of the publications, the country-wise publications. There I have quoted that in India at least, and the global data wise, publication wise at least, the waste management pattern and the resource recovery from waste, both are following the same. So that means that somehow people's perspective or how they are handling the e-waste, how they have handled the solid waste have some patterns. So if you really learn some lessons from solid waste management, definitely you can apply it for e-waste management also. So with that thought process, I just made this slide. It is completely on solid waste management. Nowhere it is connected with e-waste, but the lessons, whatever we have learned, maybe can be applied for e-waste management also. So as a part of this, one thing what we have done is national level assessment. We have kind of taken data from 100 cities and we have done the complete assessment and we have submitted the report. The another one is we visited few cities, like these 5 cities we have visited. We talked with people, we talked with authorities, and we get to know, we have taken the sample, we have done the analysis in person, and we try to know, get to know, is there any real change that this smart city mission projects has made on that particular city or people's mindset. So this is the methodology that we have followed. I don't want to go deep into it. And this is about the Indore city. Okay, Indore has this many numbers of population, all this basic geographical information and other facilities. So few photos that we have taken. So here I just wanted to highlight this 5-bin system. Can you see that 5-bin? Second photo. So there I have shown 5-bin, but here I have written 6 waste streams, right? So 5 bins are one for dry, wet, then paper, plastic, metal, and the 6th one is for e-waste. So this is the only city which has implemented 6th bin for e-waste in all the smart cities that we have visited, and all the smart city, we have talked with all the authorities, 100 smart cities authorities also we have talked with, even the people at the lowest hierarchy to the highest hierarchy, even commissioner we have talked. So none of them even move from 3 to 4. So the maximum they could achieve is 3. Indore is the only city which could achieve 5. Then 6th bin also they have introduced on e-waste collection. So how they have introduced? So when someone can do it, obviously we can also do it. When we can do it, someone also can do it, right? That is how we work. So what is the lesson that we have to learn from Indore? So to make because the e-waste management starts from its generation and separation from the beginning. So I'll just quickly move to this portion, the social impact assessment. Okay, so there are multiple things I have included, but I just wanted to highlight the social impact assessment. They have started from the base. Okay, all other people started from the top. Say they called the ward member. They told, see, this many dustbins, you distribute to your ward. So the truck is coming, you just inform your ward people to be ready with the dustbin at 7 o'clock. Everything was from the top to down. Okay, that is how they have worked, all other cities. That is how every system works, right? But what these people have done is they have started from the scratch. So they tried approaching the ward members, but looks like it was not so efficient as they have, easy and efficient as they have thought. So what they have done is they have included women into that. There are NGOs which is kind of working on women empowerment and women's better life, those kind of things, kids better life, child. So they have started with the lowest hierarchy and they went and talked to each home. Okay, and within 6 months they could see only 2 bins. Successfully they could segregate only dry waste and wet waste. So on seeing one ward, they did not start with the entire Indore city. They have selected one ward and they have successfully implemented. Then on seeing that ward, so the ward member got some prize. They have given some prize to this ward member. So then the next ward member came front and they started implementing. Now the entire community, the entire Indore city, they are very proud of the green environment that they are having. So Indore city is truly free from dustbins. Okay, you cannot see. How many of you are from Indore? Is anyone from Indore? From airport to any streets, Hyderabad is also a dust free city, but you can see dusts everywhere. There is a difference between dustbin is forcefully removed because of policy, and dustbin is automatically removed because people follow certain things. So the second thing has happened in Indore. And because of that, there are a lot of investment on Indore city. Because the city becomes so beautiful, they found lot of space to actually do lot of project. They started implementing lot of solar panel project, energy recovery project. They are making biogas and they are selling it for a nearby industry which supplies biogas to two-wheelers and four-wheelers and buses. So the story, what does it says is, the lesson is, one is changing citizen perception. Okay, it needs to be changed definitely if you want to recover anything. Okay, from waste management, awareness is very important. And when it comes to critical minerals or precious metals recovery from e-waste, the awareness not at the ground level, it has to be at every step. So they should know what is the composition. They should know what is the problem. They should know what is the environmental impact. They should know what are the technologies available. They should know everything. And strong administrative control and the support is very, very important. That is another thing that we have observed in Indore. All other cities, there is a clash between municipality and smart city officers because they want to take the name. I don't give you name. I want to take the name. I don't give you name. So that kind of. But here the good thing is Indore's municipal. That same officer is taking care of both. So in that way, one boss, rest all has to hear them. That's how they have functioned. That is one of the very big lesson that we have learned, and we have suggested the same for other cities as well for the phase 2 smart cities mission. And the another one is ICCC. Do you know what is ICCC? Did you ever hear of what is ICCC in smart cities mission? So search. Okay, I don't want to talk about that. You search. So it's a module. Multiple data can be stored, analyzed, and from there any data can be taken care of. So this is one of the another reason they act very successfully. They could get success in the short period of time. Then inclusion of e-waste management also be included as one of the pan city initiatives. Okay, so I just stop my presentation with this thing. Potential means nothing if you don't do anything with it. So every one of us have huge potential. So we need to work on something we should do if we can do it. Thank you. Lunch break.
You say the multifunctional, so we are separating the various compounds, or we want to separate it?
Separate what? Second question.
Elements are
Compounds. Then what is the another one? Elements. So it depends. It depends. So membrane is a separator. So it can separate anything. So as like whatever you are giving in a feedstock, so depends on how you have designed the membrane. It can allow, it cannot allow few things. So in that way, membrane itself is a separator. So depends on how you are designing it. So sometimes we need to go for allow moment. Sometimes we need to go for removal part. So it can be either way. That's why I told mixed solution itself is a very difficult thing to deal with. And if a particular membrane allows only two, then the two material will come into the other side. If it cannot allow two, then all others will go to that side. This two will remain in the feedstock itself. So it depends on how are we managing it. It is not about what kind of element we are dealing with, substance we are dealing with. It is all about the principle of what needs to be recovered, what needs to be rejected. Sometimes we need to go for rejection for the best recovery also. That has also happened. Yes. So if there is no energy or the system functions in a passive energy mode, if there is a stripping solution, then you don't need to put any energy. So the system functions automatically. So you need to have more solution. So your compartment has to be, both the compartments has to be filled with a solution so that the elements can move from one direction to another direction without any energy input. We can discuss more also. Maybe you can visit our lab also. Okay, there is no question. Thank you so much.
Thank you, ma'am, for such a wonderful talk.
Thank you.
So let us now have a lunch break, and after that we have tutorial session. So we have lab visit in the anatomy department. So we'll assemble at 2:30, 3:30 in the anatomy department at 3:30.